Okay, last but not least. So I'm very pleased to introduce Sid, who is, as many of you know, there are in the Indian subcontinent there are many people who only have one name. And Sid is attempting to be famous enough that he gets to claim Sid, I think. He's also trying to hide the N. So is this Sid N? That's the plan. So he did his a PhD at Purdue with Jeff Siskind. Then did a postdoc with Noah Goodman at Stanford University. Then I got my DARPA grant at Oxford too late to hire him, so I was planning to hire him as a postdoc, but then Phil Torr hired him as a postdoc instead. But instead of actually sitting in Phil's group, he sat in the middle of my group and actually did all sorts of interesting stuff to get the confluence of vision and probabilistic programming, and now has moved up the smooth seniority ladder at the University of Oxford to become a senior researcher, which means that he can actually take grants and take graduate students and these sorts of things, which is kind of nice without having to do any of the unpleasant other things that go along with being faculty. And I hilariously just learned that you also hold a position at the Alan Turing Institute as a safe and fair AI researcher or something or other. Which
is about as meaningful as calling myself senior researcher.
Which seems to be basically an ideal positioning that you've managed to get yourself positions of great prestige and authority without the political and teaching workload that usually comes with them. I was supposed to be visiting with Sid all day, and like 6 things happened, such that this is the first time that I've actually seen him, but I think he's going to sleep at my house tonight, so I'll get more, which is great. But it's going to be good, I promise. Cool. Thanks, Sid.
Right. I will actually keep this massively short, so you all can actually run away soon. The previous the talk sort of set things up perfectly, so you all know, even though you didn't know before, that you're all Bayesian anyway. So I'm going to talk about one particular aspect of it, which is the modeling side of things.
I forgot to say one thing.
Yes.
Sid's on the job market this year. And I'm trying to make him. I'm not applying any.
Do I have to teach? No. So I'm going to start by asking, why does this question of intelligibility matter? Simply because nobody seems to ever give a satisfactory answer to it, or at least how to define it. So, we've seen all the press releases and we've agonized over whether they make sense or not. But nonetheless, we've seen the press releases about how machine learning and AI are great, and everything's going to be amazing and going on in the future. So from an abstract perspective, at least, you can think of these largely as there's some observation that goes into a magical black box, and you get some decision behavior out. How you get there doesn't matter, just throw some data at it, but it exists. Right? So if you're playing Go, you might care about showing it images of the board and it tells you what to do next. If you have images of your friends, it violates everybody's privacy by tagging their faces on it. And if you're using a self-driving car, you might want to figure out who you want to run over, right? Now, that might sound sort of frivolous, but that's actually quite serious, because people do end up getting killed because of stuff like this. And, not just once or twice. And so these things speak to questions of accountability and trust when you actually deploy the system in the real world. And, of course, when you apply them in different domains, you have to care about fairness and ethics. And I snuck in work for my other title just there. And so, and in particular in the EU, which we might not actually still be part of by the time I get back, there is actually this notion of formalizing a right to explanation for any of machine learning systems we deploy. So how do you then try to make sense of this black box? We're not going to talk particularly about learning algorithms, but we are more talking about modeling. So you could think about deriving explanations largely as you have some observation that goes through a black box and gives you the decision behavior, and you have to derive an explanation that as of yet I have not defined how, but you must take as input both your observation, the decision and behavior, as well as how you went from your observation to your decision, right? So that little arrow is actually quite important. So how do people actually get there? Typically, it started getting a lot of interest in the last 3-4 years for obvious reasons. So how do people get there? Well, one way you might do it is you might say, I just throw a lot more data at it. right? So you might say, I collect data where I have observations and I have decisions, and I also go to humans and ask them for explanations for why they produce their decisions. Right? But that's really nice if you can actually go about collecting the data for it, but it has an inherent flaw in that you basically made another black box. So you had a black box that tries to explain your black box, and if you're familiar with the old statement, it turtles all the way down when you go down that road. The other thing, which is a lot more sensible, is you try to do sensitivity analyses on these things. So you go, here's an observation, here's my decision. I might just perturb the input or the output, define it by a simplified model, and try to come up with an explanation that matches. Now, largely, these are things that work in the visual or linguistic domains, and they're also things that work for fairly simple assumptions that you might make as models. They don't really, if you have that as a ResNet, you're not really going to explain it with a simple decision tree. And also, it doesn't really give you a way to fix things when things go wrong. So let's say you have a decision that you've observed, you might come up with an explanation for it, but then if you know it's wrong, you don't really have a serious way to go back and fix it. So what is a reasonable solution to this? Is there another solution at all that you could follow? Have we stuck with these? Turns out it's largely a memory issue, because we used to be able to do this just fine, right? And this is old AI, which is probably too old for most people to care about. But the thing is, if you did start with something like interpretable abstractions, if people are familiar with Shurudlu or anything else, then you could actually define decisions and behaviors and explain them precisely because the abstractions that you developed for the data you observed was interpretable. And so it's not quite that simplistic. And to give you a very quick example, I'm going to run through very quickly a version that we did a few years ago. Well, not quite just a few years ago, but a little longer than that. But it actually does do really well. And the idea is you want to do captioning for video. Okay. There should be video playing, but it's not. Assume there's some action going there, and that's the actual caption that's going on. Use your imagination. So we had this thing where we went, what happens if we can actually extract features out of this in some non-deep learning framework? This is no deep learning involved in this, so that's the caveat. Okay, we can do pretty fun stuff with it. So it turns out what we could rely on then for learning, which was in SGD, was dynamic programming. And you could do the Viterbi algorithm that people would most likely be familiar with. And so you can take detections from your videos, build up a tracker lattice and ask to do tracking. You can take the same things, compute features off of them, and do event recognition. This is the old way to do event recognition and tracking. And the nice thing about this particular framework was you could actually combine them together using factorial HMMs, however you want to think about it, which was still polynomial time. So we had these really nice polynomial time algorithms to do event tracking and to do entity tracking as well as event detection simultaneously. And if the videos did play, well, you'd see that if you tracked with an event model versus just tracked on its own, the tracks sort of end up making a little bit more sense. I'm not quite sure why the videos aren't playing, but I don't want to futz around with it, it's fine. And so the question then is, you can actually expand this to a much larger set. You don't have to do activity recognition as just verbs. You can actually take a whole grammar, build lattices for the entire thing, and then decide to do this huge factorial HMM thing. Now, all of this is largely besides the point. It's mainly to show you that it's possible to build up abstractions to do complex tasks that people can claim to do now, but you can do it in such a way that you can actually get away with getting interpretable abstractions. So, effectively this ended up in a bit of work called the sentence tracker, where you had this nice way of scoring a pair of videos and sentences to come up with inputs and outputs, and you could track them and you could score them and you could do a whole bunch of things with them. I will skip this in the interest of time, but we could do pretty fancy things out of it. But obviously, the most important question there is, how do you actually take that sort of idea and combine it with the scalability of neural nets? So what we would like to do is take the much richer behavior that was possible before with those kinds of systems, but in a restricted domain, but scale them up so that you can actually do those same kinds of fun behavior in larger data. And that's basically what my brief in the last 3-4 years has been in trying to figure out how to get this to work. So if we go back to the original framework, we can actually then think about a third way of how you can do explanations by tying together these two pipelines. So you might go, some observations, there's some bit for me to get interpretable abstractions. But once I have that, coming up with decisions and explanations becomes a lot more easier for me to reason about, right? And now you might say, but you just moved the goalposts a bit. The black box that was there is now sitting there. That's not quite the case, because you've freed up the reliance on your decision directly on observations, you can come up with constraints about what your interpretable abstraction ought to be. And the thing that, at least that I care about is, particularly when you're looking at things like perception, is you can actually think about what it's intended for. So when you think about explanations, you're actually providing explanations to humans. And so coming up with abstractions that have common ground with the kinds of explanations you will have with humans is actually a very powerful constraint on the representations you learn. Another thing is, because you can actually use the same abstraction to do multiple tasks, it gets you to generalize a lot better as a framework. And you obviously can go back and forth with this. It gives you a mechanism to intervene in the system as well, because you can now do explanations with it. So the question really is, that particular path of going from observation to abstraction is a really important question to figure out if you want to deal with interpretable, explainable AI systems. So we've seen this sort of spectrum before. You can go from, I don't care about any I don't care about actually doing any sensible modeling, just throw data at it, to the complete other end, which is I will only do decision trees, in which case you're not going to scale your data. Right? So the nice thing is you can try to apply the principles from human perception, like core concepts from Spelke, or you like recursion and composition from Jack and Off, into the kinds of models that you use to specify these systems, and then use those constraints to learn flexibly somewhere in the spectrum. So how do you operationalize this? Well, you want to go from observations to abstractions, and you want to use those abstractions to provide explanations. At least in the cases that we care about in this instance, the observation domains are perceptual, your explanation domains are also perceptual. You're observing images and videos and language, and you're talking about things in terms of what you can show in the image or language. And so a nice framework for this is effectively the autoencoder. So you have some encoding that goes into an abstraction, you can decode that abstraction into an explanation, and because we actually care about the kinds of abstractions you want there, and you put a regularizer on it, I'm massively oversimplifying it, but you can think of that as a variation of autoencoder. I don't want to necessarily go into explaining these things. Quickly, I'm going to run through the three things we've sort of been dealing with, how to actually regularize those abstractions so you get interpretable representations out of things. One way you can think about it, which was along with Frank as well, is what happens if you actually have abstractions where you might have some labeling for the kinds of features that those particular data points capture. So if you had so for example, for that image, if I knew that was Tim, that's useful. If I knew where the lighting for that particular person was and I didn't know who that was, I can feed that in. So I have a sort of disparate source of data where I can, for some data points, I have some ideas about different aspects. And the nice thing is you can actually combine this all into a single framework where after learning, you can figure out that one particular aspect of the representation corresponds to a meaningful semantic concept like identity. And another one might correspond to lighting, right? And the contributions here was mainly, we sort of come up with a nice, clean framework to do all of this in, that you can actually write fairly complicated models that capture the different kinds of relations between the features you might care about in that particular data. Second one is, if you didn't really have any way of supervising, but you knew broadly what kind of structure the latent representations ought to take, you could then figure out how to actually enforce that. And here the idea is you would like to figure out how to get independent factors. You would like to say, I would maybe get sparse factors on the data. And the nice thing is, you can actually apply that in a way that, I don't want to go into too many details, but basically if you've heard of the beta VAE, it doesn't really get you what it says it does. Okay? That's the takeaway. It doesn't really do any disentanglement. If you want to do disentanglement properly, you ought to be a little bit more careful in what you're dealing with. That's the underlining really helps. And effectively, the idea is you don't always want to think about independence as disentanglement. Disentanglement is largely this idea that you want to capture conditional independence. And in some cases, that conditional independence is conditional independence of factors given your data. but realistically you might want to capture conditional independence between latent variables as well. And the way to do that is actually think of a more general objective than just independence on your latent space. Right? And finally, this is what we just presented here at NeurIPS. What happens if you actually say, I'm not going to put in any constraints directly on the latent representations, but I'm going to constrain them to capture information coming from two different modalities. And the reasoning behind that is images are largely unstructured sources of information, but text is structured. So if you try to encode images and text jointly in some sensible fashion, the question is, do you actually get any structured representations out of it? So that's the overarching question here. And you might want to factor this in terms of colors and the parts of the birds, because that's what the sentences encode. So the idea is there's some abstraction that you observe in different modalities, and you would like to recover that particular abstraction. So the thing that most people are familiar with when dealing with multimodal data is largely domain transfer. People really like this idea of going from one visual domain to another, but then if you are actually capturing faithful generative models of multimodal data, you ought to be doing a lot more than just going across. Right? And so the question in this particular work was at least to set it up so that you could learn to factorize your latent representations in the structured manner I was talking about earlier. You should be able to do joint generation. You should be able to use multiple modes of information to do better estimation on any one. And so that's where this thing was set up to go. And turns out not a lot of people actually care about all the questions. Largely only care about cross generation, as you can see with all the ticks in that column. So here's a simple example. Zach mentioned earlier that there is this MNIST VAE example, and it's just a toy example to show you what happens if you have digits that are the same on both domains, but how you draw it is completely different and specific to each domain. And so you would like to encode both of these things jointly, so that you would like to learn a factor that corresponded purely to digit, one factor that corresponded to how you drew the MNIST digit in particular, and one that corresponded to how you drew the SVHN digit. And of course, you would like to go backwards from the unconditional latent space. You would like to generate the data so that you make sure that you are actually capturing the fact that the digits are the same. And you would like to do the cross generation, and hopefully observing both gets you a better objective than observing any one. So I won't go into too much detail here, but basically there's a version of the importance weighted autoencoder you actually have to use, because the estimator, you need to be careful about the estimator not overbalancing importance weights on different modalities. But if you sort of be careful about that, then assuming a mixture of experts approximation to your joint posterior, which is what you need because you need to go down each modality separately, gets you pretty good results. That's what the final objective looks like. And so here are some pictures. Those are generations from the MNIST model and Streetley House number model, and you'll see that the digits do tend to line up quite a lot when you're learning this properly. That's reconstruction on each domain, cross generation. And this actually does do a lot better than the previous version that tried to deal with this, where you basically get nothing. Right? There's a massive data imbalance issue that you have to deal with when you're dealing with actually trying to only tie together the latent space. Everything else is still independent. There's some experiments to show that there are actually latent dimensions that correspond only to one dimension, only to the other, and do both. And you can do this really interesting experiment where you do a single bit VAE and you show what happens if you build a linear classifier off of the latent space. So if you just build a normal VAE for SVHN and you build a linear classifier off of it, you get pretty poor classification, which says that the latent space hasn't really factored into any particular region that captures the digit. But if you do both together, you get much, much better. And you can also do this thing where you take an off-the-shelf classifier, classify the MNIST and the SVHN separately, and see if the digits match. That's testing whether the joint generates properly. And the cross, and I won't go into too much. You can refer to the paper for further details. And we can also do this reasonably well for the images. it's not quite great, but the point isn't really, unlike the GAN space, the point here isn't really like picture perfect generation. It's much more to look at the latent space to see if you can figure out what's going on. And we have some preliminary experiments with that in the paper. I won't go into too much details there either. Things seem to work. It's largely a first step in trying to figure out if we can actually get representations that are meaningful by forcing multimodal integration.
What's the language model?
Huh?
What's the language generator and into it?
It's actually ACNN. It's not an LSTM. You basically assume independent generation for words. This language model isn't really complex enough to need anything else. It's largely conjunctions of really simple phrases that are adjectival, so you don't really need too much of history for this. But it works surprisingly well for a CNN.
Do you use some sort of embedding?
No, we learn the embedding. There is no pre-trained embedding.
No, for the word, for each word.
Yeah, we learn the embedding. There is an embedding matrix that's actually learned for this. So none of this is pre-trained, except some of the image generation stuff here, we actually do use ImageNet features directly, and generation is nearest neighbor in the train set. So these examples look better with obviously doing nearest neighbor. These ones are actually generated. And there are multiple copies because when you do generation, you sample both from the prior and the likelihood, not just the mean of the likelihood, and that's why you have multiple samples there. And you can see that in some cases you will get some difference because of the likelihood, for what it's worth. Yeah, and so just to finish up, I'm sort of going along this line of we would like to find sensible ways of incorporating human knowledge about the world in ways that step up in complexity. So we've been considering a taxonomy so far, where you constrain values, you constrain the structure, and then you try to figure out if you can do this later. And currently, I'm working with a student on trying to find much more principled and more generic constraints that might be able to capture some of the rules, like along the lines of Bayesian program learning. And that's it. Thank you for all the collaborators. And any questions if there are? Thank you.
Long day, but there's still time for questions.
All right. Thanks very much. That was a very interesting talk. I was wondering about your incentive behind using a linear classifier to classify like a highly nonlinear but disentangle or factorize the latent space.
So the expectation is that if your multimodal information is helping separate out a part of your latent space into the digit part, for example, then it should only be at best an affine transform away because it is actually being separated out.
Sure.
And that's why I apply a linear classifier.
Sure, but that latent space is built on top of a highly nonlinear space, right?
That's fine, but that's why the comparison is to a unimodal VAE. You're still doing the same nonlinear transformations to get to the latent space.
Right.
It's just that the constraint of observing two different kinds of data that correspond to the same underlying information constructs a latent space that's more amenable to a linear classifier than not.
Sure.
And that's the implication.
Right. Thanks.
Yes?
So the fact your internal representation is tuned for explanation means it's not going to be as good as if you didn't have.
That's not necessarily true. So there is, ICML this year, there was the paper that got Best Paper Award is one that effectively the claim is, and it's recycling. It's a recycling of an old ICA result by Aapo Hevarinen, which is for any given objective, you have an equivalence class of representations that can get you that objective, and the kinds of inductive biases you put into your model may shrink or expand the class of representations you can get there, but it doesn't necessarily say there is one unique element in that class of representations that gets you the best objective. And so all of this is an attempt to find a different point in that space of equivalence class representations that is more human amenable. That's it. So I don't necessarily think it means you will lose performance, but empirically sometimes because of the assumptions you make elsewhere in the model, you can lose performance sometimes. So for example, CNNs aren't really that good for producing human-like representations because you're not completely spatially invariant. The sky isn't down in an image and things like that. So those kinds of modeling assumptions you might make as part of your framework can actually hurt if you try to go to something that's more human amenable in the representation space. But that's largely, I wouldn't say, I'd say that there isn't necessarily a reason to presume that going to a human-like representation will hurt you performance-wise.
Yeah, more constraints on it, so you can optimize as well. The obvious reason.
That also, I mean, that's because you're using STD or whatever. If you weren't using STD, you might not get there. I'm much more interested. I view those things as much more as tools, and I'm happy to throw them away if they don't suit my purpose.
So I just have a question of sort of human sort of this representation that's human amenable, right? So depending on the task, the type of explanation you might have might be different, or who is your target, right? Like
Yes.
So how do you feel that integrates into this?
I would expect that integrates as part of the, at least the way I'm viewing it, I'm expecting that to come in as part of the interaction with the system. So it's not just a one-way thing to go from the abstraction to an explanation. You also do allow people to talk to the system through that framework. So that you can actually say, let's say you're doing a computer-aided diagnosis thing, and you have some way of, say, finding a tumor in a scan. That for a computer vision person might be there's a little bit of blurriness in this particular part of the image. Now, to a doctor, that's not necessarily going to help much as an explanation. So you'd have to find a way to ground the term, say, some sort of feature that's familiar to the doctor in terms of the blurriness that you observe in the image. And that's really where we would go to and say, you would have a, hypothetically, none of this is actually there yet, but you would have to say something like, the practitioner goes to the system and says, that bit there looks like a nodule of some sort.
So you're basically saying we should over-specify the explanation, and then out of sort of the over-specification, for a specific explanation type, you would pick out the bits that are...
Over-specification is one, I suppose that's true, but then it's also, the way I'm looking at it is it's also much more a lossy compression you're trying to, lossless compression you're trying to do. Most of the time, if you're doing things like classification or regression, you are doing lossless compression. You're basically going to a label space that discards some information that the original input has. And the reason why this sort of autoencoder framework is useful is because it is trying to do compression, but it's trying to do lossless compression. And so technically, that abstraction that you learn should contain all the information that's relevant to regenerating the input in the first place. And so the only thing that the context really changes is the form that the particular representations will take. So you wouldn't necessarily have lost any information at that point. So, yes?
What does the stuff that you said about explainability affect verifiability? If we imagine a few years
affect
ago,
what?
Verifiability.
Right.
Let's say we start having legal requirements for systems.
Oh, yeah.
Right? I mean, you have exactly the same problem.
Sure.
But you don't want to just nudge the representation, the constraints in some direction. You want to enforce that something is there, really.
Yeah.
But maybe specifying this is actually at least as hard.
That's true, but that's also a legal problem, not necessarily a machine learning problem.
Do you think those problems will be from technical side the same thing, or is it different?
No, I wouldn't expect them to be the same thing because the consideration, like for a machine learning system, once you've defined an objective, it's that. Like say I want to do person identification for faces, that's the objective. If I have to define a legal framework around that, I have to make sure I'm not being biased about certain things. And talking about that is different. How you would specify that as a legal framework does not necessarily have to be how you would define the objective for the machine learning algorithm.
I'm asking, like, you're almost getting there to my question. It would not be specifying the objective, right? It would be specifying something which happens while you're optimizing or after the fact.
Sure.
So it would be some way of interrogating the system.
Yes, and that the interaction is important. So it's not, you do also want to go back in there and manipulate the system to see if it's actually doing what you expect it to do. So I haven't talked about like the causal inference part of things, but this should allow you to actually go in there and do interventions on the model to see if you get the requisite output that you would hope to get out of it. And so I think it's a fairly general but not overly constrained framework to deal with this. And the really difficult question is trying to figure out what level of constraints you can place on it. Because the only things I've seen so far are either they're too restrictive or they're not restrictive enough. And so we're still trying to figure out where to go in that Goldilocks zone. That's the sensible.
Have you ever tried thinking about sort of feedback loops? Whereas, like, you have this observation, you make some decision, right? So my decision maker could always be quite bad, and
Yes.
I could have like any explanation, a sound explanation for a very bad decision maker.
Yes.
But does it tell us anything about some knowledge about the actual world that we're trying to make the decision on?
I wouldn't say that's feasible if you only looked at it as an automated system. I think if you chucked a human in the loop, then you'd be a lot more sensitive. You could be a lot more reasonable about it. But I don't necessarily know if the answer is, if I could give us a single answer in the general case. I'm sure we'd have to deal with that on a slightly more case-by-case basis.
Okay.
So I'll spare us all the technical question that I would like to ask, and instead suggest that we give a round of applause and ourselves a round of applause for doing effectively a mini NeurIPS symposium the day after NeurIPS is over. So good job, all of you. Thank you very much. And